The graphs of direct variation are a little bit different depending on the exponent that you have. But mainly we're going to be looking at y equals kx versus y equals kx squared. The reason why is because most of the situations that you will be exposed to are either in the left form or the right form. Most of the time we don't realistically have too many direct variation equations that have an exponent greater than 2. So we're just going to kind of stick with this graph. But the main thing here is we need a kind of a little bit of a refresher again, a little bit on what the graphs look like, how to calculate those graphs and those kinds of things. To start off with, if we're looking at y equals kx, and I'm going to work mainly with that side first, remember that the k actually is our slope. If you don't remember how to find the slope, remember y equals, or the m equals y minus y over x minus x. With that being said, again, the k represents the slope of the line, so that's your rise over your run. And I want to just talk to you briefly about, how that k can be affected in terms of the equation of the line. When we're looking at the graphs, and I pulled up 3 different graphs here. If you notice, the red graph is going to be that y equals x. This graph here has a slope of 1. If I look at the blue line, this has a slope of y equals a half x. Notice with that half x, it's smaller than 1, so the slope is not as steep. And the green line here is a y equals 4x, so it's extremely steep in comparison to the blue line and the red line. So as that number gets closer and closer to 1, the steepness or the slope of that line is not going to be as great. So just something to note there, and like I said, that should be a refresher there. When we're dealing with a y equals kx, this is, k doesn't necessarily represent the slope. K represents, it's kind of related to slope. K represents how wide the graph is. And that's something that we just need to look at. It's not something that is realistically going to affect things too much. If we look at the y equals x squared graph here, this is a normal y equals x squared. If I pull up a second one here, let's change the k value. So there I have a y equals a third x squared. So this actually took the arms of that parabola and extended it wider. So if I'm going to use y equals 3x squared, as you can imagine, this is actually going to make the arms go in. So the larger the number, the closer the arms of that parabola come to the y-axis. The wider it gets, the smaller the number is as a fraction. So just something to note there. So that's going to be our parabola. With our y equals kx squared, you can either have a min or max, depending on your situation. And we could see that based on our graphs that we had coming back here. We had a minimum there at 0, 0. And this is just our vertex. Again, you're just looking for your min or max. Also talking about reflection, where's the line of symmetry? This is where you're going to cut your parabola in half, which in this case, for both of those, it's going to be at the y-axis. Otherwise, it's just a basic, you're just graphing these different situations in order to figure out how wide or how steep certain graphs are, depending on whichever direct variation equation that you are working with. The other thing to consider with the y equals x squared, sorry, I'm going back to this a little bit, but the slope, it's called a rate of change. And it's basically the same thing that you would do for a slope equation. It's just a little bit different in the fact that it's called a rate of change. Sorry, that I know is something new, and I forgot to review that with you with parabolas. And so, again, difference. One's a line, one's a parabola, one deals with the slope, one deals with the rate of change. And you're just looking for how is that graph different than if it were a regular k value of 1.